can be considered as very high frequency vibrations. So a low pass filter is a device, actually, electronics, that allows low frequency signals to pass unchanged while killing high frequency oscillations and therefore killing noise. And we've learned about frequency response and body plots. If I have a device that has amplitude ratio 1 and phase lag 0 at low frequencies, what does it do to low frequency signals? Well, Y prime ultimate is the same as the signal in, since the amplitude ratio is 1 and the phase lag is 0. So if the ultimate isn't changed, it will not change. So that means that those signals are passed unaffected. What does it mean killing high frequencies? Meaning making the amplitude disappear, making the amplitude 0. So we want something that has amplitude ratio 1 for low frequencies and amplitude ratio highly negative at high frequencies. Okay? And that's a low pass filter. And a transfer function that accomplishes that is the following transfer function. With two parameters, tau f and n being an integer. What is the body plot of that transfer function? As omega? Yes.
It goes to 90, because there's no delay. Right?
That was a rhetorical question. It doesn't go to 90 with any end. It goes to minus 90 times n is our signal. The body plot of this transfer function here is log omega. So here is log omega goes to infinity. In other words, omega goes to 0. This way, omega goes to infinity. This way, this is a transfer function that the AR plot has low frequency asymptote log of the k it has for n equals 1 would be first order without time delay. And we know that has log absolute value k as we hit as omega goes to 0. So log 1, in other words, the amplitude ratio goes to 1 at low frequency. And it has a quarter frequency at 1 over tau f. So here is log 1 over tau f. And first order would go with slope minus 1 in the log log. In the log log. If I have n, actually the slope becomes minus n. So the higher the n, the faster high frequencies get killed. Okay? Remember, that's a log scale. So the AR goes 10 to the minus n down. Okay? So it goes really fast down the side. What about the phase lag? As we would like, at low frequency, omega goes to 0, phase lag goes at 0. Okay, here is 0. Okay. At very high frequencies, it reaches an asymptote minus 90 times n. So it will reach an asymptote at minus 90 degrees times n at the, and by the way, this is called the breakpoint frequency, 1 over tau f.
I thought it was called corner. I thought it was called corner frequency.
Say again.
I thought you called it corner frequency. Corner frequency?
It is a corner frequency. It would be because it's an intersection, but this particular corner frequency pertains to filtering. It's called the breakpoint frequency. It is a corner frequency whenever we have low frequency and high frequency asymptotes meet, whatever transfer function we have. This particular corner frequency is called the breakpoint frequency. Okay? When it applies to filtering. Okay. So, let's see. Oh, yeah. All right. And at the breakpoint frequency, it will be minus 90 times n. So, okay? So it has the desirable characteristics. At low frequencies, signal is not getting changed. At high frequencies, the amplitude ratio disappears. That means that if I have a signal that looks like that, and here I have two frequencies. I have the frequency of the noise, which is a high frequency, and I have the frequency of the oscillation that you clearly have there. That's a high frequency. So this is the unfiltered signal. The filtered signal will kill the oscillations of the noise, but will leave the oscillation that you're seeing, and there will be some phase lag depending on how high the n is and where the tau f is, so it will be a little bit to the right, indicating a phase lag. Any other question?
Yeah, if n is 2, does it go to 180, negative 180?
Yes, exactly. If n is 4, it will go to minus 360.
Okay.
So, what about the choice of n? There's a trade-off here. The higher the n, the faster we kill high-frequency noise. However, also, the bigger the lag, which is not good. So the penalty we pay for low-pass filtering is lag. And, yes, sir?
Right on the angle side, minus 90 degrees, minus 90 degrees again.
Yeah, the first is minus 90 times n. The second one is minus 90 times n over 2. Okay, at the corner, it's minus 90 times n over 2. At the breakpoint. Clear, everyone? Question? Kim? Everybody right? So we have a trade-off. Obviously, the higher the n, the faster we kill noise, but also we produce more lag. The usual choice of n is 1. Okay? but there have been higher order plus filters used.
Is the corner supposed to be at like the top of the horn, or like at the top of the little 90? Or is it could be anywhere?
The corner is where the low frequency and the high frequency meet, and they meet at 1 over tau f. So how would you do the asymptote? You would start with log 1, and you would find log 1 over tau f, and where they intersect, you would draw a straight line of slope minus 1. Better now?
Yeah, and just, you see the like the 90-degree angle, the negative end that you drew?
Yes.
Is it supposed
The white axis is for the white line. The orange axis is for the orange line. So you have, okay, this, maybe I should put the 0 there. So here is 0 here, okay? At minus 9, at the breakpoint frequency, it's minus 90 times n over 2, so if n is 1, minus 45. And the high frequency asymptote for phase level is minus 9. Rim question.
Yeah, I was going to ask about 91, there's 290, but you just say like because...
One is times n, the other is times n minus 2.
Yeah.
n over 2.
I felt like a 90.
All right, times.
Okay.
Does that help? Would it
Yeah.
be dot?
Yeah.
All right. Anybody else? All right. So the useful choice is n equals 1. All right. So now let's talk about adding derivative action to the control. Ideal PID has the form u prime of t equals kc error plus 1 over the integral time constant, integral of the error, plus derivative time constant, derivative of the error. And if we Laplace transform this, we get the transfer function Vc of s equals kc 1 plus 1 over tau is plus tau d times s. This has two issues. Number one issue, it can never be physically implemented. It has, if you make common denominator, it has higher degree numerator than denominator. That means that if I have, for example, a constant signal, if E bar is, for example, constant, which would be 1 over s, that would make the result. Okay, so if E bar is 1 over s, then GC E bar would be same order numerator and denominator. Which means I'll have a response that has infinity. You can't implement infinity, guys. So it's not implementable. Okay? You can't actually make this. You can probably make an approximation of this, but you cannot make this. However, that's not bad, because actually we don't want to implement this guy. Because if I have derivative action and I have a noisy signal, then what is the derivative of something like this? the noise. And the result of implementing this would, if we could have implemented it, mathematically you can implement it to saturating whenever you give a value, okay? The result of this would have been controller that goes like that. So, valve would be banging on and off, on and off, on and off, all the time. The system response would be a disaster. Your valve would need replacement every day or so. So, you wouldn't want to do it anyway. So two things, we can't do it, and in any case, if we could, we wouldn't want it. What is instead implemented is this times a filter. So, and how much we filter depends on how big tau d is. If tau d is tiny, I need to filter only a little bit. If tau d is huge, I need to filter a lot. Makes sense, right? So, what is implemented is let me put here PID F as a superscript. This is new notation I'm producing right now to make the notation that it's a PID with a low-pass filter. That is what is normally implemented. N equals 1. Actually, most commercial controllers, and you can check the one book that has this is the Seaborg Edgar Mellincham book. And you will have that the most common form, or a common form for commercial PID is not directly this, but I will show you that this is equivalent to that. And I will see the equivalence. So the commercial PID common form is what is this?
PI.
PI. And then you have something called a lead lag. Tau d s plus 1 over alpha tau d s plus 1. So that tau d, as I will show you, is related to the derivative tau constant, and that alpha is related to the tau. Let's call this tau 1. Let's call this tau 2. Star 1 and star 2 are equivalent. So let me show you the equivalency for star 1 and star 2. Now, I will say something. All the tuning of the methods that you have seen is done for derivative action, or the recommendation, Ziegler-Nichols, or, well, not for Ziegler-Nichols, you could put actually the filtering. Yeah, that would have been a better way. But anyway. But all those are based typically on ideal PID. The Cohen-Kuhn is based on ideal PID. Another method I hope I will have the time to introduce today is also for ideal PID. So we will have